This lesson is on graphing the sine and the cosine function, and you'll notice it said part 1. We're going to do these graphs in detail and learn everything that we can about graphing the sine and cosine function before we move on to the other trig functions. Before you do this lesson, you should be sure that you understand radian measure of angles, that you understand the concept of circular functions, which you should have already looked at, and that you have a good understanding of the values of special angles of the sine and the cosine function. Our first problem is to graph y equals sine x. Now, whenever we graph on an x and y axis, you might recall that the x-axis is a real number line and the y-axis is also a real number line. So these are real number values. That indicates that we need to use radian measure for this x so that we're using a real number here. Recall that a radian measure is just a real number value. And so we'll be finding the sine of that real number x, and it will give us a real number y, and then we will plot those points. Now, normally, when you don't know anything at all about what the graph of a function looks like, you start by selecting some values of x, substituting into your equation, and finding the corresponding value of y. So you might think about making a table of x and y values. And most students like to start with x equals 0. So you might recall if x is 0, the sine of 0 is 0. Now, some of the special angles that you had, for instance, in terms of degrees, was 30 degrees. But recall in radians, 30 degrees is the same thing as pi divided by 6, isn't it? So if we choose the real number pi divided by 6, we know the exact value of the sine function for 30 degrees or pi over 6 radians. We know that is 1/2. One of the other special angles that you know is 45 degrees, which recall in radians is pi over 4. So the real number pi over 4 gives us a sine value of square root 2. Another special angle, 60 degrees, is pi divided by 3. So the real number pi over 3. And recall the sine of that is the square root of 3 over 2. Now, obviously we could keep choosing these values, but what we're finding are real number values of both x and y, which we're going to locate on this graph. Now, I have gone ahead and set up a table similar to the one that we started constructing here. You'll notice on this table I have listed for x values 0, pi over 6, which recall is 30 degrees, pi over 4, pi over 3, pi over 2, 90 degrees. Now, here is where we're going on over into the second quadrant, if you will, when you think circular functions. Recall when you did the circular function idea, you said this is 0, this was pi over 2, and as you rotated this direction, you're coming over here to pi. So we're going on between pi over 2 and pi, and then we will continue on around. So I have gone ahead and selected these angles that have our special angles as reference angles all the way through. Now, you'll notice right above this pi over 6, I have a 0.5. If you take your calculator, using your pi key on your calculator, you can take the value of pi, which of course is about 3.14, but your calculator will have more decimals. Divide that by 6, and I just rounded off to the nearest tenth, 0.5. I did the same thing here. My pi key divided by 4, rounded off is about 0.8. And of course, pi is 3.14. It keeps going. Notice I've said that is about 1. It's not exactly 1. It's a little bit more than 1, but we're rounding off because we're going to locate these values. I have also listed down here the values that we know. The square root of 2 over 2, square root of 3 over 2. At pi over 2, we have a value of 1. 2 pi over 3 has a reference of pi over 3. And we're in the second quadrant where the sign is still positive, so square root 3 over 2 again, and so on and so forth. Okay? Now, below, like the square root of 2 over 2, I've done the same thing with my calculator. I took the square root of 2 divided by 2 and rounded off, and that was about 0.7. The square root of 3 divided by 2 rounded off was about 0.9. Now, what I want to do is to take these values that I have listed here, and we're going to plot them on this graph. So let me scoot this up so perhaps we can see these values as well as our graph down here. Okay, we're going to start where x is 0 and y is 0. That, of course, is our origin right down here. When x is pi over 6, or approximately 0.5, y is exactly 0.5. So on my graph, I'm going to estimate an x value of 0.5 and go up to a y value of 0.5 and mark that point. When x is pi over 4, or roughly 0.8, my y value is square root 2 over 2, or roughly 0.7. So 0.8 would be just before 1, 0.7, so we're not quite up to 1 yet. Pi over 3 is approximately 1, and the y value is about 0.9, so we're not quite up to 1 yet. At pi over 2, which is approximately 1.6, notice my y value is exactly 1. Okay? Now, you'll notice as we keep going, I'm going to go to an x value, 2 pi over 3, which is approximately 2.1. You'll notice I'm at square root 3 over 2 for y, which we said is approximately 0.9. So what's happening here is that my y values are starting to decrease. When I get to approximately 2.4, my y value is approximately 0.7. At about 2.6, I'm on 1/2. And at pi, which is about 3.1, I'm back on 0. Now, if you look at the part where we've put these little points so far, we started here, we came up, hit 1, and we came back down, and we're back on 0, just a little bit beyond an x value of 3. Okay? Now, I continued from there, going on over into the third quadrant. Notice when you pass pi, you go into the third quadrant, and remember in the third quadrant, our sign values are negative. So 7 pi over 6, which is about 3.7, has a negative 1/2 sign value. 3.9 has a negative square root 2 over 2, which we said is about 0.7. When I get to 4 pi over 3, which is about 4.2, I'm at negative square root 3 over 2, which is about negative 0.9. At 3 pi over 2, or roughly 4.7, I'm exactly on negative 1. Then notice as I continue, now I'm going over into the fourth quadrant. 5 pi over 3 is about 5.2. And my y value is negative square root 3 over 2, or about negative 0.9. When I get to 5.5, 5.5, negative square root 2 over 2 is about negative 0.7. 11 pi over 6, or approximately 5.8, I'm at negative 1/2. And then when I get to 2 pi, which is going to be about 6.3, I'm back on 0. So if you followed those points, our graph came back up here. Now, those are all of the values that I've found, but I want to talk a little bit about this idea of circular functions and how that relates to what we're doing. Remember, if we make a complete revolution, we have come back around to 2 pi, but we can keep making revolutions. And of course, what happens as I complete a revolution, I'm going beyond 2 pi. So I would take 2 pi plus, say, pi over 3. 2 pi is 6 pi over 3 plus pi over 3 is 7 pi over 3. Now, if I take my calculator and take 7 times pi and divide that by 3, that's approximately 7.3. Now, what do we know about the sign value? Well, it's going to be the same thing we had at pi over 3, isn't it? Okay? So what we learn as we continue this direction, we're going to run through these exact same sine values that we did on our first trip around the circular function. So this function, as I continue going this way, would repeat these values over and over and over. Now, what happens on a circular function if you rotate in a negative direction? Well, you get a negative angle, don't you? If we go to the left of x equals 0, then we're getting negative values of x, or if you will, negative angles. Now, as we go this direction, remember our first few negative angles are going to give us negative sine values. And we're going to stay negative until we get to negative pi. Negative pi is approximately negative 3. What would happen here, again, is we would run through all of those same sine values, but we're sort of doing it backwards. Now, what we see occurring is that this sine curve, as we call it, keeps repeating itself sort of as we move along the x-axis in both directions. It keeps going up and down and up and down and up and down. You probably also remember that the sine of an angle, any angle, is always between negative 1 and positive 1. And we see on our graph that we never go above y equal 1 or below y equal negative 1. That's because our sine values always stay between 1 and negative 1. Now, obviously, every time that we graph a sine function, we do not want to have to go through all of these points. Of course, we're going to become very familiar with the general shape of the sine curve. What we usually do is we pick out certain key points on our sine graph. Now, I have listed here what we consider to be the key points. Notice I have when x is 0, y is 0. When x is pi over 2, y is 1. When x is pi, y is 0. 3 pi over 2 gives us negative 1, and 2 pi gives us 0. If you look on the graph that we have just done, I picked out the 0, 0 point, the pi over 2, 1 point, the pi 0, the 3 pi over 2, negative 1, and the 2 pi 0. Those are 5 basic points that we consider for the sine graph. Now, anytime then that I want to graph the sine function, I'm going to start over here. I'm going to use these key values. The first one is 0, 0, so I'm going to plot that point. Now, I'm going to skip over for a second and look at the point pi 0. Pi, we know, is about 3.14, so just a little beyond 3, we're on 0 again. I'm also going to pick up 2 pi. Well, 2 times 3.1 is about 6.2. Now, if you keep more places, it really rounds off to about 6.3. Our y value is 0 again, so we're going to go over here to 6, just a little beyond, and we're on 0 again. Okay? Now, pi over 2 is halfway between 0 and pi. So if pi is about 3, that's going to be pretty close to 3 halves or 1 1/2. So pretty close, just a little bit probably to the right of that, our sine function is on 1. And then 3 pi over 2 is halfway between pi and 2 pi. So halfway between pi and 2 pi, and you can estimate that, we're down on negative 1. These 5 points give us sort of our key points, and from those we can do our little sketch of our curve along here. As the sine function goes up, it's sort of concave downward. We call this curving this away. It curves on down to here. When it gets to this 0 point, it starts curving up. Okay? Now, this is what we call one period of the sine graph. Now, what exactly do we mean by a period? Well, let's look at a definition of a periodic function. A periodic function has the form f of x equals f of x plus p for all x in the domain of f and for some positive number p. The smallest number p for which this is true is called the period of the function. Now, this notation may look a little foreign to you if it's been a while since you've been in algebra. All you're saying is if I add a certain amount to x, and this is a constant value, I get the same function value that I had before I added that constant value. Now, here's what I'm going to illustrate here. We know that the sine, let's just say, of pi over 4 is square root 2 over 2. What happens if I take pi over 4 and add 2 pi to that? In terms of a circular function, here's pi over 4. If I take pi over 4 and I add 2 pi, I'm just going to make a revolution and end up back in the same place. So the sine of pi over 4 plus 2 pi is also square root 2 over 2. In fact, for any place that we are, if we add 2 pi, it just means we're doing a revolution to that, and so we're going to get the same y value. We have a complete cycle of our sine graph occurring between 0 and 2 pi. Now, this is approximately a distance of 6.3. If I go from 2 pi another approximate distance of 6.3, this graph is going to repeat itself. Or if I take that distance of approximately 6.3 and I map it out over here, I'll see another repetition of this graph. Because of the values of these circular functions, and just as we make revolutions, we just repeat our sine values, all of our trig functions are going to be periodic functions. They're going to repeat in values. The sine function repeats every distance of 2 pi, and so we say it is a periodic function with a period of 2 pi. Now, as we go back to this graph, and I'm again just sticking with this one period, I know that the graph would repeat on both sides. The other thing I want you to notice is that as we move along this graph, the largest point we ever hit is 1, and the smallest point is -1, and all of our values are between there. We're going to see a similar occurrence with our cosine function. Now, at this point, I just want to review a few concepts. When we're asked to graph a sine function, usually we'll only graph one period, and then we know that the graph will repeat. I want to emphasize these special points, and you will soon become very familiar with these special points, because these 5 basic points give us our rough places where we're crossing the x-axis and our high and our low points. And then we use those points to sketch in the shape of our sine graph. Now, we're going to do a similar process and graph the cosine function, but I am going to speed this up a little bit. I have already prepared a table of values for the cosine function, again using the special angles that we're familiar with and getting the appropriate cosine value. Now, you might recall with the cosine, if you think in terms of going around the unit circle, the cosine is positive in the first quadrant, then it's negative, negative in the third, and finally positive in the fourth. And you see that being reflected here. Remember, pi over 2 is right here. Then you see the values becoming negative, staying negative till we get around here to 3 pi over 2, and then becoming positive again. Now, as we did before with our cosine, or with our sine values rather, we sort of narrow this down. Let me see, I'm losing it here. Here we go. We narrow it down to specific points. The 5 basic points we talked about on the sine function: 0, pi over 2, pi, 3 pi over 2, and 2 pi. So we're going to use these 5 basic points and plot those on our graph. our first point, let me show you again, was 0, 1. When x is 0, y is 1. Okay? At pi, remember pi is about 3.1. We're at negative 1. So I'm going to come over here at about 3.1. We're down here on negative 1. At 2 pi, or about 6.3, we're on 1. And notice at pi over 2, which again is halfway between 0 and pi, we're on 0. And halfway between pi and 2 pi, at 3 pi over 2, we're on 0. So at about 1.5 approximately, a little bit more than that, we're on 0. And halfway in between here, we're on 0. Now your cosine graph sort of curves concave downward to this 0 point. It's coming down like this. Then it's going to curve more upward as we go here, and then it'll start curving more downward again. Now, exactly as with the sine function, if we continued rotations, this graph would repeat itself. Okay? So the cosine graph is also periodic. It has a period, we say, of 2 pi, just like the sine function. This distance between 0 and 2 pi, we have a complete cycle of our graph that repeats itself. Also notice on the cosine function that we're never above 1 or below negative 1. That's because the values of the cosine of an angle are also always between negative 1 and positive 1. Now, before we look at another definition, I want to just emphasize here, as I was doing this table of values for both the sine and the cosine, you'll notice I was very careful to use radian measure. We talked about they need to be real numbers, and getting their approximate decimal equivalent, and then doing the same thing on the y values. If you do not use the same scale on the x-axis as you do on the y-axis, you will distort the picture of your graph. So I'm going to encourage you, as we do all of these graphs, to always use the same scale for both the x and the y-axis. Now, we have defined a periodic function. Basically, it just means that the function values repeat themselves for some specific value of p. And in the case of sine and cosine, that's 2 pi. Also, though, we have what we call the amplitude of a periodic function. The amplitude of a periodic function is defined as capital M subtract little m divided by 2, where capital M is the maximum or largest value of the function, and little m is the minimum or smallest value. Now, with this cosine function, our maximum value is y equal 1. Our minimum value, is y equal negative 1. So, according to the definition of amplitude, I take my maximum value of 1, subtract my minimum value of negative 1, and divide by 2. Now, of course, this is going to become plus a positive, so I'm going to get 2 over 2, or 1. Basically, this amplitude is giving you the maximum distance away from the x-axis that your graph is. Of course, with our sine function, we would get exactly the same thing, an amplitude of 1. Now that we have looked at just the basic sine and cosine graph, we're going to look at what if there's some additional numbers involved in this equation. So this next one that I'm going to look at is y equals 3 times the sine of x. Now it's real important that you understand the order here. You're going to find the sine of x and then multiply by 3 to get your y value. Let's recall our special values that we mentioned earlier. I want to use x equals 0, pi over 2, pi, 3 pi over 2, and 2 pi. Those are my 5 special values. Now, we know that the sine of 0 is 0. and 3 times 0 would still be 0. We know that the sine of pi over 2 is 1. 3 times 1 is 3. We know the sine of pi is 0. 3 times 0 is 0. We know the sine of 3 pi over 2 is negative 1. 3 times negative 1 is negative 3. And finally, the sine of 2 pi is 0. 3 times 0 is 0. Now, let's plot these points. I have 0, 0. I'm going to go ahead and do the pi, 0, and the 2 pi, 0. You'll notice for pi, it just went a little beyond 3, 2 pi a little beyond 6. At pi over 2, about 1 1/2, our y value is a 3. And between these two, halfway, our y value is negative 3. Now, what happens is that the basic shape and characteristics of your sine graph are the same, but what's happened is because of this 3 in front, it has stretched our y values. So in other words, where our sine function used to be on 1/2, it's on 3 halves, 3 times 1/2. So it has stretched our function up and down. That means it has changed the amplitude. Now I'm abbreviating it. On this graph, our maximum value is 3, our minimum value is negative 3, and of course if we simplify this we get 6 over 2 or 3. Notice again, 3 is the maximum distance that I'm ever away from the x-axis. And notice, and this is not a coincidence, 3 is also the number that happens to be here. So what we're learning is if we have a sine of x with a number in front of it multiplied times that sine x, this number will change the amplitude of our function. It will just stretch our sine graph. The period is still the same, notice, because we're still getting those zeros in exactly the same places. Now again, if I needed other periods of this sine graph, I would just start repeating what this graph looks like. Graph y equals negative 2 times the cosine of x. Notice here we have the cosine of x being multiplied by negative 2. Well, as we did before, I'm going to talk about these special values of x. Again, we use 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now remember, when x is 0, the cosine is 1. 1 times negative 2 is negative 2. When the cosine is pi over 2, when the x is pi over 2, the cosine is 0. Negative 2 times 0 is still 0. If x is pi, the cosine is negative 1. Negative 1 times negative 2 is positive 2. 3 pi over 2 gives us a cosine of 0 times negative 2 is 0. And finally, the cosine of 2 pi is 1 times negative 2 is negative 2. Now again, let's plot these points. 0 gives me negative 2. I'm going to do pi next because it's about 3 and I get a positive 2. 2 pi is a little more than 6 and I'm back on negative 2. Now halfway between 0 and pi, approximately 1 1/2, we're still on 0, and halfway between pi and 2 pi, we're on 0. So my graph is coming this, and then it's going to curve like this and come down like this. Now, let me just sort of illustrate a couple things that has happened. Here is one period of the cosine graph. Now, what did that negative 2 do? Look at your shape on this graph. Well, this negative did what? It caused our basic shape of our cosine to flip upside down. But the 2 also stretched our values. Now, I want to talk a little bit about amplitude here. Remember, amplitude is always defined as the maximum value. Well, our maximum value is 2, minus our minimum value is negative 2 divided by 2. If we simplify this, we get 4 over 2, which is 2. Now compare this to to the number that's here. You'll notice the 2 is the same thing as our amplitude. We do not call amplitude negative. So when we see a number in front of the sine or the cosine, sometimes we say that the amplitude is the absolute value of that number. Amplitude is always given as a positive quantity. We do want to take note if that number is negative, because that will flip our graph upside down. Okay, I want us to look at this example, y equals the sine of 1/2 x. Now the difference between this example and these others that we've been doing is that the number is inside the argument of the trig function. Look at the difference. Here 3 is on the outside, it's times the sine function. Here we're multiplying 1/2 times x, and then we're finding the sine value of that. And by the way, while I'm here, I sometimes have students who try to factor that 1/2 in front. You can't do that. The only way you can change this argument is with an identity. And so we don't want to be messing with that, if you will. Now, I want us to look at what happens if I start using those same 5 basic points. I'm sorry, I'm thinking 0 and needing to write an x. 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now, if x is 0, 1/2 times 0 is still 0, and the sine of 0 is 0. If x is pi over 2, 1/2 times pi over 2 is pi over 4. So right here, you're doing the sine of pi over 4. Well, the sine of pi over 4 is square root 2 over 2. Okay, let's look at this one. If x is a pi, you're doing 1/2 times pi, which means you're doing the sine of pi over 2, and the sine of pi over 2 is 1. Okay, if x is 3 pi over 2, and we multiply by 1/2, we get 3 pi over 4. So we're doing the sine of 3 pi over 4. Well, all that's doing is putting us over in the second quadrant. When you think circular, it's still positive, but it's square root 2 over 2. Look what happens here. If x is 2 pi, 1/2 times that would be a pi. The sine of pi is 0. Now let's plot those points and see what has happened. I have 0, 0. I have pi is 1. And at 2 pi, I'm on 0. Notice at pi over 2, square root 2 over 2, if you recall, was a little bit more than a half. What I have is just sort of the upper half of one cycle of my sine function. What I want you to notice here is, notice if I go to 4 pi for my sine value, what's 1/2 times 4 pi? Well, it's 2 pi. Sine of 2 pi is 0. Now, 4 times pi, if you take your calculator and do 4 times about 3.14, or just use your pi key there, is about 12.6. This is about 12.6. We've covered a distance of about 6, so you'd need another distance of approximately that same amount. Now I'm just going to kind of estimate. My graph doesn't go that far over. 1, 2, 3. Okay, so here is 6, 7, 8, 9, 10, 11, 12. Somewhere along in here, I would be back on 0. In between these values, if I take half of numbers between 2 pi and 4 pi, I get numbers between what? I get numbers between 1 pi and 2 pi. And remember, between 1 pi and 2 pi, our sine values are negative. So the negative parts here, let me just put in the 3 pi right here. If I do half of 3 pi, I've got 3 pi divided by 2, and the sine of 3 pi over 2 is -1. So at 3 times pi, or a little bit more than 9, let's see, this is 7, 8, 9, a little bit more than 9, we're going to be down here on negative 1. So what has this 1/2 done to our function? Well, it has changed the period, okay? We are no longer doing one complete cycle of our sine graph between 0 and 2 pi. It took us a distance from 0 to 4 pi to get one complete up-down cycle. You'll notice our amplitude is still 1 because we never get above 1 or below negative 1. So if we have a number times our x before we do our trig function, that's going to affect the period of our function. Now, what you can do is to realize that on a normal sine function, if we take x between 0 and 2 pi, we get 1 period. X being the argument of just y equals sine x. If I take 1/2 x and put it between 0 and 2 pi, and I solve for x, if I multiply everything by 2, 2 times 0 is 0, 2 times 1/2 x is x, and 2 times 2 pi is 4 pi. I'm seeing that as x ranges from 0 to 4 pi, like we show in our graph, I will get one complete cycle of my graph. Now, as the other periodic ideas, this graph would continue and have other periods repeating those y values. Now, let's look at sort of a summary here. Finding the period of sine or cosine. In y equals sine x, x ranges from 0 to 2 pi for one period of the graph. In y equals sine times bx, notice I have a number times x, bx will range from 0 to 2 pi to give us one period. So, to find the period, set up the inequality 0 is less than or equal b times x is less than or equal 2 pi. Solve for x. The way we'd solve for x is divide everything by b. 0 divided by b is still 0. bx divided by b is x, and then 2 pi divided by b. So this tells me that between 0 and an x value of 2 pi divided by b, I will get one complete cycle or one complete period of my graph. The period then will be of length 2 pi divided by b. And I've just mentioned a similar calculation works for the cosine as well. Now, how am I going to graph in general then a sine or a cosine that has one of the forms we've looked at? To graph one period of the sine or cosine, place the argument of the function between 0 and 2 pi, solve for x. This gives the beginning and end of one period. Divide this interval into 4 equal parts and graph the function using the amplitude and the 5 basic values. Be sure to consider whether the function is flipped upside down or not. In other words, do we have a number in front of that sine or cosine that is negative? Now, this may seem sort of overwhelming at this point, but we're going to put all of this together and show you that you can get a sketch of a sine or a cosine fairly quickly using these guidelines. I want to graph y equal cosine 2x. I'm going to make a couple of notes. The first thing I'm going to notice is that the amplitude is 1. How do I know that? Because there is not a number here in front of the cosine function. Since this is not just an x, this is called the argument of my cosine function. I'm going to put that argument between 0 and 2 pi, which is usually what my x would range over. Now I'm going to solve for x, so I need to divide everything here by 2. So as I divide by 2, 0 divided by 2 is 0, 2x divided by 2 is x, and 2 pi divided by 2 is pi. This tells me that I will have a period of pi. In other words, over a distance of about 3.14, I will do one complete cycle of this cosine graph. Now, what I want to do is mark off my beginning point is here at 0, and my ending point is going to be at 3.14, okay, between 0 and pi. Now, I know that at the beginning of a cycle of my cosine graph, my cosine value is 1. And notice if x is 0, 2 times 0 is still 0, and cosine of 0 is 1. Notice at the end of my cycle, if x is pi, 2 times pi, cosine of 2 pi is what? It's 1. So I'm going to end up at the end of my period on 1. What is halfway between 0 and pi? Well, it would be pi over 2. Okay? 2 times pi over 2 gives me pi, and the cosine of pi is negative 1. So at pi over 2, or about 1.5, I'm going to be down here on negative 1. Okay? My period begins at 0, it ends at pi, and halfway in between those is pi over 2. Now, what's halfway between 0 and pi over 2? Well, if I take half of pi over 2, I get pi over 4. Okay, pi over 4 is going to be just approximately 3/4, and that's where I'm going to be on 0. Okay, what's halfway between pi and 2 pi? Now, I'm going to do this for you. If you need to find halfway, it's like finding a midpoint. To find a midpoint, you add the values together and divide by 2. So pi is 2 pi over 2, so adding here I get 3 pi over 2 divided by 2. If you divide by 2, it's the same thing as multiplying by 1/2. So 3 pi over 4 would be halfway between my pi over 2 and pi, and that's where I'm going to be on 0 again. So my cosine graph is going to have the same shape as the regular cosine. It's going to have the same amplitude, but notice my period has changed. I'm doing one complete cycle between 0 and pi. Now if I wanted additional periods, then I could just repeat this graph over the next unit of, or next interval of length pi. Okay, let's graph this one. Y equals 3 times the cosine of 1/2 x. Okay, well let's see. First of all, notice this number here. What's that going to do? Since my cosine values are normally between 1 and negative 1, if I multiply by 3, they're going to be between 3 and negative 3. So my amplitude is going to be 3. Notice the argument is not just an x. So I'm going to place the argument, 1/2 x, between 0 and 2 pi. Now this time, to solve for x, it'd be easier if instead of thinking divide by 1/2, if we think multiply by 2. 2 times 0 is 0. 2 times 1/2 is 1x. 2 times 2 pi is 4 pi. Okay, so our period is going to be 4 pi. 4 pi, remember, if you do 4 times 3.14, it's about 12.6. Okay? Now, since my period is going to be 12.6, and I don't have that many squares, I'm going to move my origin over here. So we're going to consider this to be my y-axis right here and scoot that over so I've got plenty of room. Now, here's what we want to do. My period begins at 0 and it ends at 4 pi. What's halfway between 0 and 4 pi? Well, it'd be 2 pi, wouldn't it? Okay. What's halfway between 0 and 2 pi? It would be 1 pi. What's halfway between 2 pi and 4 pi? That would be 3 pi. This is what we meant in that little sketch about taking our period and dividing it up into 4 equal parts. Okay, so I'm going to start at 0. I know that the cosine at 0 is normally a 1, but because of this, multiplying by 3, it's going to have a value of 3. So when x is 0, I'm going to get a 3. The cosine of 0 is 1 times 3 is 3. Now, at the end of my period, at 4 times pi, or about 12.6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, about 0.6, we're going to be back up there. Okay? Notice 1/2 times 4 pi is 2 pi. The cosine's 1 times 3. Same thing. Now, halfway between those is at 2 pi, or about 6.5. 6.3. 1, 2, 3, 4, 5, 6.3. That's where our cosine is down, normally on -1, but because we had a change in amplitude, it's going to be down on -3. At pi, 1, 2, 3, we're going to be on 0. And halfway in here, which is 3 pi, it's about 9. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, a little bit more. We're on 0. So our cosine graph will come down like this, and up like this. And we have graphed one period of this cosine function. Notice how the cosine shape is still the same. We've increased our amplitude, and our period really stretched out to cover a distance of about 12.6. Graph y equals -2 times the sine of 2/3 x. Well, again, let's talk about amplitude. Remember, amplitude is always positive. So amplitude is going to be the absolute value of this number we're multiplying times the sine function. Our amplitude is going to be 2. Now, what exactly does that tell me? It tells me I'm going to be up 2, down 2, but never more than 2 units away. The argument is not just an x, so we're going to take our 2/3 x, place it between 0 and 2 pi, and we're going to solve for x. Now, I'm going to do this in 2 steps. First, let's multiply 3 by 3. 3 times 0 is 0. 3 times the 2/3 would cancel the 3, and I'd have a 2x. 3 times 2 pi is 6 pi. Now, we need to divide by 2. Okay? I apologize for this camera. I don't know why it's doing that. It's acting up today. Okay, so our period will be a distance of 3 pi. Okay? 3 times pi is a little bit more than 9. Let me just kind of do that with my calculator right quick. It's about 9.4. Okay? Let's see. I'm going to scoot over a little bit, maybe not quite as far. Let me move my y-axis over to about right here. Let's let that be our y-axis. My period will begin at 0, okay, and it's going to end at 3 pi. What's halfway between 0 and 3 pi? Well, it's 3 pi divided by 2, okay? What's halfway between 0 and 3 pi over 2? Well, it's going to be 3 pi over 4 if I take half of 3 pi over 2. Now, to get this halfway between these two, remember we take 3 pi over 2, add 3 pi. 3 pi, remember, is 6 pi over 2. So when I add, I get 9 pi over 2, and then we want to take half of that and divide by 2. So this is going to be at 9 pi over 4. Now, the reason I'm finding these is sometimes they will ask you specifically where these values are, and you need to be able to find them. We will be approximating a lot of this. Okay. 0 is here, and 3 pi is about 9.4. 1, 2, 3, 4, 5, 6, 7, 8, 9. About 0.4 is going to be about right here. Now, this is a sine function. I'm thinking my sine graph normally looked like that, didn't it? The 2 is going to change the amplitude, and what's the negative going to do? It's going to flip it upside down. Notice if x is 0, 2/3 of 0 is still 0. The sine of 0 is 0. -2 times that is still 0. We're still going to be on 0 here. We're still going to be on 0 here. Halfway between those, at 3 pi over 2, we're still going to be on 0. Now let's see. Let's do 3 pi divided by 2 is about 4.7. 1, 2, 3, 4.7. We're going to be on 0. Now, estimate between 3 pi over 4, and sometimes I'll do a quick estimate like this, like if pi is close to 3, this is going to be about 9 over 4, and 9 divided by 4 is just going to be a little bit more than 2, isn't it? Okay? So somewhere along in here, and I'm going to come down here. Now, normally the sine graph goes up first, but because that's negative, it's going to come down, and because of the 2, I went down 2. Now, halfway between here, at 9 pi over 4, and again, you can sort of do a quick estimate. 9 times 3 is 27 divided by 4 is going to be how much? 4 times 7 is 28, so it's a little bit less than 7. 1, 2, 3, 4, 5, 6, 7, somewhere along in here is going to be our halfway, and we're going to go up to 2. So our sine graph will come down, and then it will go up. And again, if you needed additional periods, you could, of course, complete those. Now, I hope from this lesson what you're beginning to see is that there are certain basic characteristics of our sine and our cosine. They have an amplitude, and that amplitude is affected by any number that is multiplied times the sine or the cosine function. They also have a period. Normally, if it's just sine x or cosine x, that period is from 0 to 2 pi, distance of 2 pi. If we have a number multiplied times the argument of our sine or our cosine function, that changes that period. So I want us to, again, emphasize that you need to look at the amplitude, you need to look at the period, and we've illustrated how to find our new period. Once you have that period, we're dividing it up into equal parts, and that's to use those 5 basic values. And then we take into consideration the amplitude and whether the graph is flipped or not to get the sketch of the graph. We will be continuing our study of sine and cosine graphs in another lesson.